Okay, good morning, guys. I'm here today to reproduce that exercise from yesterday. I figured out what did happen with my NanoHub CompuCell application there. It was a problem with the configuration, so that's why nothing was happening today. I'm sorry for that, but today let's see if we do in a different way. I will go through the exercise showing how they are, what things you should do to build the models, okay? Again, let's start not from the very beginning, but since James has presented this lecture today about the modeling, that first slide of yesterday, when I introduced the problem of cell growth and cell division, talking about cell cycle and what metabolic routes that the cell has to follow to enter in a event of division and proliferation. I will go directly for the implementation of the cell growth and division in the CompuCell3D. Okay. This first slide I already talked about yesterday. James also has talked today about if you want to build a model, you have to analyze everything from your experiment to reproduce the best as you can the situation. And although you have to build the model in function of these observations you do, okay? Of course, we always start to build models in the simplest way. Usually the simplest way is the best way. So the rules must be simple at the beginning, then as long as the initial model works, you implement the features in the model to try it, including more features, more properties of the cell, of the system you are observing and trying to reproduce. Okay. Cell growth in CC3D is very easy to implement at first sight. You just have to add to the volume target of the cell at the beginning a constant factor that will promote the growth at each time interval you decide, maybe 1 Monte Carlo step. This is done in the steppable file. Here is the volume, the control volume, the plugin volume is loaded in XML file, but since you have to change parameters during the simulation, this must be done in the Python part, in the steppable file. And this is very easy. Now, this first box here shows you the plugin volume name that is added at the XML file. And the second box is the place in the steppable file where you define the initial values for volumes, target volumes, E lambda volume, the volume constraint for the plugin. And in the step function, you make the change you have to do in the volume, in target volume. This 0.001 here is the G in the expression above, sorry. Let's see how to implement then this cell growth in CC3D. The first exercise, we have the first task here. Create a 5x5 single cell simulation in a 100 square grid. As properties and behaviors, you include in your code this contact, surface, local flags, volume local flags, plugins, and the growth steppable. Okay, set initial cell lambda volume to be 3, and the growth rate to be 25 voxels per 500 Monte Carlo step. Okay, let's go to the NanoHub or desktop if you have, and try to build the simulation. Maybe you can do that in 2 or 3 minutes. I wait.
Remember to use the poll.
Yes, which one is the correct poll? Is model.
Exercise completion.
Okay. Okay, most of them, they have, okay. I think it's okay. I will show you here after everybody close the wizard in the two edits. This is what we see after closing the wizard. So you identify here the places you have to change to build your simulation, to finish build the simulation, to change the lambda volume to 3 and the growth rate to 25.
Gilberto, sorry,
Yep.
Gilberto,
Yep.
if you hear background noise, hit mute all and then unmute yourself. Gilberto, you have to unmute yourself now.
Mute myself. Here are the modifications you should have done. Here in the left window, you change the radius to 5 and the width to 5 for the 5 by 5 single cell you have to create. In the center of the grid. In the right window, you changed the cell lambda volume to 3, and in the rule for the growth, you write the 25 over 100 factor for the rate, growth rate, okay? So now you run the simulation. Open your browser or your player, and this clicking the step button, you should see the small cell 5 by 5 at the center of your grid. Please, I wait for you for only 1 minute to have some evolution in your simulation. And this is what you have to see while the simulation is running. We have here 2 snapshots. And if you don't have those kind of images in your simulation, please let us know. Everybody finish this one?
I must have done something wrong. I don't have it.
No? What's the problem?
I have multiple cells.
Multiple cells? Then maybe you didn't in the XML file in the blob initializer. Let me go back here. Here, you have to put 5 and 5. The radius must accommodate only one cell.
Yep, got that.
Okay.
Those changes.
Also, you have to change the lambda volume to 3. Don't forget that.
Yep, got that. My player crashed also. Let's get it back. It's possible I failed. Okay, I must have failed to save again. Sometimes the save doesn't work, but I'm okay now. Sorry.
Okay, no problem. Let's go. Now we go to the second exercise in this one. You have to, in the steppable file, you add a target surface constraint and an initial targeted surface of 20 and lambda surface of 3. In the right window here in the image, you see the place where in the steppable, where are the attributes for the definition for the volume plugin. So this is the place where you have to add similar lines like those, just change volume to surface with those values, 20 and 3. In general, when you load the surface plugin, it doesn't put the lines that the when you load the surface plugin, it doesn't put the lines like that in the steppable. It's a kind of difference of the volume plugin. The volume plugin, they are there already. You have to just plug it, change the numbers. But the surface plugin, you have to type. Okay, that is the change. You add 2 lines with the values proposed in the exercise.
Oh my God.
What happens?
That's okay. Keep going, Gilberto. I think somebody just unmuted by accident.
Okay. So then you run the simulation. So run the simulation. You see what happens. Please answer the poll to see if who is doing the exercise. I wait 1 more minute, then you can observe the evolution of the cell. And that's is what you see. Since we have this constraint here in the oh, see, I forgot, I wrote the wrong word here. It should be surface here, sorry. Anyway, with the surface constraint of 20, is the cell cannot grow accordingly the volume, because this constant limits the size of the cells to be a straight line. So the cell grows as a square. It grows because you always has a probability to grow, even if the energy is not, the variation in the energy is not adequate. The Monte Carlo step, the Metropolis algorithm, allows that your system have a chance to grow even with forbidden energies. This is a statistical stuff, okay? So this is, we have to adjust this target volume, surface, lambda surface, to allow that this cell grows properly. Let's see that, how you do that in the next part of the exercise. So now we assume that the cell must grow like a circle, a disk. Okay, so we have as a surface, which is a perimeter in 2D, a perimeter of the circle, which is a circumference of length 2 pi r. So you have to change the growth rate of the cell according with the changes in the target values of the cell, of the surface cell. Try to do that. Okay, so you have to add a line here in the bottom part of the screen, the right image, to allow that the target surface of the cell changes accordingly with the volume of the cell, the target volume of the cell, because the target volume of the cell is increasing with this amount per Monte Carlo step. And so far in this image here, the cell target surface is constant. So you have to allow the target surface grows accordingly with the target volume. And that is what happens here. This is what we have to include. I mean, to include a new line where we are saying that the surface of the cell, which is in reality, the perimeter of the cell grows with the radius of the volume. Actually, the radius of the disk, the circle, because a volume here is in 2D is a surface, an area. Okay, so 2pi r is square root of the volume. So doing that, we can run the simulation and see that the evolution of the system now comes back to a more circumferential form. I mean, the length of the perimeter grows according the volume, the inner area of the cell. Did everybody get this images in your simulation you're running? If you don't, tell us. Please answer the poll. Okay, this is a very easy example. Now we're going to advance and go to the next step in our model, that is the division, the cell division. Okay, what triggers cell division? We saw what triggers cell division. We saw yesterday about cell cycles, cell entering in different phases, and basically when the cell decides to divide, it is in some cell cycle. But yes.
Sorry, before we move on, we have a raised hand here.
I have to scream. Sometimes it's difficult to see.
Yeah. Sarana, if you want to go ahead and ask your question.
What is the question?
I was responding to the poll.
Oh, okay.
And so it said raise your hand if you needed help.
Oh, okay. If you want to send me a direct message, then we can work that out. Unless you have something that you'd like to
Oh,
share.
no, I'll email you directly. I'll message you directly.
Okay.
May I continue?
Yeah, go ahead.
Okay.
Well, now I've got another raised hand. Bharat, is it related?
Okay. Bharat?
Yeah. So my doubt is basically when you do not account for the increase in surface area, you do not increase your target surface with the increasing volume. Why does the cell adopt a circular shape and then increase over it? Why can't it do it in a circular fashion? Why can't it just add more circular rings at the boundary and then just keep increasing? Why does it become a squarish cell first and then does that?
I don't know if I understood. You are asking why the cell without this updating target surface grows differently when we have the constant value for the cell.
Yes.
Because
why does the cell become square first? That's my, like, why does it opt to become, isn't being circle the smallest surface it can achieve? So why does it become a square first?
Because the square is with the square thing, we have this the linear straight lines to the boundary, and the straight lines are the smallest have the smallest length. Since the target lambda, the target volume, the surface cannot grow, it's fixed. It tries to keep it the smallest value possible, and the smallest value possible is a straight line.
Okay. I think I understood. I got confused between surface
If
area.
you have more availability to grow, then it can becomes round. circles.
Right. Makes sense. Yeah.
No, but I want to say something. You've raised a good point. You're on a square lattice,
Oh, yes, sure.
and a line is shorter than
Oh,
a curved
okay.
surface on a square lattice. This is a lattice artifact.
Right.
If
That
it-
makes
if
so
it-
much sense.
If it were,
So if you
if
use
it
a
were-
hexagonal,
if you were on a hexagonal lattice, you'd get a hexagon.
I see.
And if you were on off lattice, you would get a circle, because
Right.
the minimum perimeter for a given area is different on a lattice from what it is in free space. So that's a
Okay.
very good observation. Thank you.
Thank you.
Okay, so let me see here. We saw this movie yesterday just to see again what is mitosis in a cell. And that was our objective. I mean, not so ambitious like we are seeing in the movie, but we are going to divide the cell. So we have a lot of substeps in this. The cell has a lot of substeps to produce these two daughter cells. But a lot of the substeps involve a cell having structures, which we don't have so far. So we are going to try to model a very simple cell with no structure. And the basic assumption is, okay, let's put some rules for the cell to divide. Let's say the cell divides when it reaches the double of its initial volume. It can be anything, but this is the one, because we are supposing that the two resultant cells after divisions are the same at this first model. We have the same cells, it's just a cell dividing itself, so it produces two equal cells. Of course, you can, after, decide if you want two equal cells or two different cells, or one equal or another different, so far. It's a matter of the system you want. To implement this division, the CompuCell has a stepable called mitosis. The structure of the stepable we are going to see now, but it involves blocks when we can adjust the properties of the cell and the behavior of the cell during the division or after the division, like target volume, surface types, properties, mutations, if you want, a lot of things. And this is triggered in the simulation by the way you want. Okay, you can say at the beginning we are going to divide the cell by time, which means that we are going to choose some amount of Monte Carlo steps, and between this amount of at the end of each amount of Monte Carlo steps, we are going to see if there is cells to divide, and then we divide it. Sure. This is the structure of the stepable. It's a class loaded in the wizard when you are building your simulation. It has the first block here, where you define the event that triggers the division. You make a list of the cells that are which obey this rule to divide. We put this cell in that list, and we choose the orientation of the division. I mean, you can divide a cell randomly. CompuCell by random choose a plane in the cell, through the cell, a radial plane in the cell, and divide the cell in that plane, half to each side of the simulation. Okay? Or you can define other planes of division. You can, if a cell is some kind of elongated, you can choose a different axis to divide the cell. The second block here is where you update the things. I mean, first you say that just before the division, you reduce the volume, the target volume of the cell which is going to be divided by 2. Could be any value there, but here, remember, we decide to divide by equally. You divide by 2, and the second line, you clone the parent cell to a child cell. I mean, you create a new cell exactly equal to the parent one. The only difference between those 2 cells are the IDs. They have to be different. CompuCell doesn't allow you to have 2 objects with the same ID in the code. So any object have its ID. But it can be completely equal in properties, behaviors, anything. Okay? And the last part is the way you choose to divide the cell. I mean, if the both cells are going to be equal or are going to be different, or they are going to be have mutations if you want, anything. In this part here, you see here, we are dividing the cells by default. The mitosis steppable by default, divide the cells into different cells if you have it at the beginning of your simulation, of course. Okay? So this is the mitosis steppable. Now, here is the detail of this steppable. Here we have cells to divide. Just to passing through more quickly here. Here you have the condition. I mean, you iterate of all the cells in your system, this line here, and see which ones are greater, have volume greater than 50 voxels. If that's the ones they have, you include in the list. This is the first block in previous slide. After that, you have the division. You make a loop over the cells in the list of the cells which are going to divide. Choose an orientation. By default, the orientation is a random orientation in the steppable, and you update the volume for the parent and clone the child. This is the steps you have to follow, the basic steps you have to follow to implement mitosis in a CompuCell simulation. This is a thing that you have to call for attention, because sometimes if you call two steppables, if you include 2 steppables in your simulation, the variables that you define inside one steppable cannot be used in the other steppable. But you can share these variables with this command inside one steppable. The ones you want to share with another steppable, we will include this line in your first steppable. Okay? This can be used. It's very, very handy, because otherwise you have to define things many times. Okay, this is what you would see in a division. Before the mitosis, you have only 1 cell. After mitosis, you have 2 cells. The green here is the parent cell that remains, and the blue one is the new one. The blue one is the child cell. Okay. Remember, in biology, daughter cells are the terminology to speak after cell division. But here in CompuCell, we keep using this new terminology, such as parent and child cells, just because the child cell is copied from the parent cell. So the parent cell is the cell that exists before the child being created. So we keep this terminology just to keep track of the origin of the properties that we are passing from one to another cell. Okay?
We do have a quick question in the chat, Gilberto. Can you explain how the self.parent cell is created?
The cell, it's machinery inside CompuCell. You say that cell has to, the cell green here has to be divided. It is in the list to divide. Let's go back a little bit. Oops. Previous. No, one more. Here. If the cell is in the list to divide, which is, for example, if it has the volume more than the double of the initial volume, it enters in this list. And here, the cell, it's divided. Self-divided random orientation cell. The cell which is in the list is divided by the machinery inside CompuCell. This is internal stuff in the CompuCell. We don't have direct access to this division. We can change properties, we can change attributes, behaviors, but the division itself is controlled in this block here for cells to divide. Okay, did I answer your question?
A little bit. So pretty much the self-parent cell, is that the cell that's like predefined to have already divided?
Yes, the parent cell is the one that exists, that is the one that's growing.
Okay.
When it reaches the volume you determine, it is includes in that list for division.
Okay, since I was just a little bit confused because it wasn't explicitly stated like within a dictionary or something like that, that the parent cell is equal to like this ID or the parent cell is like equal to like the list of cells to divide.
No, the ID is created by CompuCell.
Okay.
The original cell, the parent cell, has its own ID, but when it divides, the second cell, the child cell, gets a new ID.
Okay, got it.
Okay.
I have a question regarding the division. So let's say we have a SPML model attached to a cell. If it is divided, does the SPML model would be available in the child cell?
You have what attached to the cell? I didn't understand.
Yeah, I said that let's say that you have a SPML model, subcellular model attached to a cell. So the cell is divided. Does the child cell will have the same model?
I mean, you are saying that if the cell has an internal structure, for example, how to divide the internal structure? Is that's what I ask?
No, about
it's a property.
About subcellular model like antimony model that we can add.
You mean if there is some field attached to the cell?
No. When you clone a cell, when you do division, all of the attributes that you have created are copied, including any SBML models.
SBML.
So
okay.
anything you add as a dictionary or anything else that you add explicitly to the cell will copy. The only thing that will not copy will be links. And Julio and Priyam will go over that on Thursday and Friday. But everything else that you have attached to a cell as an attribute will copy. when you use the clone parent to child function.
Oh, okay. Thank you.
Okay, let's implement the cell growth and cell division now in this exercise. It's basically the same kind of beginning of the exercise, the previous exercise, but now we are going to create two cells, stem cells and a non-stem cells, a terminally differentiated TD cell. For the simulation, we are selecting contact, volume effects, growth, and mitosis. Don't need surface plugin now. We set both lambda volumes to 5 and both growth rate to 25 to 500. But at the beginning, the initialization state, the initial state is only a single stem cells in the center of the domain. Try that, please.
Do you have a question from Norma about whether it's possible to create a new way for a cell to divide? Can you override the cell division function, I think is what she's asking.
Let me read. Sorry. A new rule for division?
Norma, do you want to clarify what you mean by that?
Yes, I want to know if it is possible to, to create another proposal about how cell is dividing.
What would you like to do that's not available now?
I see.
No, what is it you would like to do?
Well, first I would like to know how this function about division was built. And the other thing is I would like to know if I can basically based in some things that I have some experimental evidence about how cell is dividing. I would like to add that function or to use or to propose a function to test that idea.
Well, so the answer, of course, is that you can do these things, but the question is, what is it that you would like to be different? So the mitosis steppable creates a new cell, one new cell, and it divides the pixels or voxels that belong to the parent cell into new voxels that belong to the parent cell and new voxels that belong to the child cell. And you have 4 options that you can use. You can divide along a random axis, along the major axis, the minor axis, or along a user-specified axis. If you wanted the cell to divide simultaneously into, say, 4 cells, or you wanted to have a specific type of allocation of voxels, then you could define that independently for yourself.
Okay, then I think that is what I need. But
Right.
yeah, I would like to work on this idea in the hackathon, so probably I can explain later.
Great, perfect.
Thank you.
Daria, was there a question also? Anyone else?
I think I answered the one about the blob.
Okay. I think in general, you'll find that the basic module is quite flexible, but for very sophisticated things, you can certainly extend it.
Okay. Okay, after you finish your wizard, this is the how your simulation looks like. In the left image here, since you have two kinds of cells at the beginning, the blob initializer will write those two types here in the line 43 of the image here, ST and TD. Look, in general, as a default, the radius of the blob is 20, and it always put here the types of the cells you created in the simulation. The proportion, I mean, how many cells they are going to, the initializer we're gonna write in the first step of the simulation is half and half. So if the radius accommodated, I mean, 50 cells, then you probably will have 25 of each type here. If you want to initialize it, create more type, more than for one type than the other, you repeat this the type here. For example, you could write ST, TD. This way, it will divide the space available, the circle of 20 voxels radius, in 2/3 to ST cells and 1/3 to TD cells. So you can handle the initial state here by changing the amount of times that the cell type appears in between these tag types. Yeah. Okay. In the right window, we have the original values, the default values for target volume and lambda volume. Okay, and the standard, the default value for the growth in the last line. You have to now to change this to set the values in the exercise, proposing the exercise. I think you already did that, so I'm gonna advance here because this is what you're gonna have. You change this here for radius 5 and 5, and keep only ST cell type, only the ST cell at the beginning, and the size of the radius accommodates only one cell, ST. Okay. And here you change the lambda volume to 5 and the growth rate to 25 over 500. Now, just to have a look in the mitosis steppable, it was loaded with those default values, cell volume above 50, and two different cell types being created after division. This is the standard implementation of the mitosis step. Now we can run the simulation. Go ahead.
Can I see the code again?
Sure. The step up, the mitosis, or the whole
This one.
This one?
Yes.
Ah, okay. See, it is loaded this way. I didn't make any changes in that step up. We are going to change later.
Oh, I see. You're just highlighting it.
Yes.
The red box.
Yes, I just highlighted to see, because we implemented two cells, then we are having two different cells after each division. This is the default way. So this is the simulation that you must have seen. At the beginning, you have just one single cell in the center of the grid. When the simulation runs, the cells start to divide and the whole blob grows because the number of the cells is increasing after divisions. Okay. Do you guys get that? Oops. Okay, I think the time is already passed, then that allows you to see the configuration, the final configuration here. If you keep running, it will fill the space. We are going to see what happens with that also later. Okay, so now we are going to change the rules. One of the rules. The first rule to change is change the condition for division by setting to 30 here and run the simulation. This is very easy. So you go to the code, change just one number, save it, and run again. This is what you have to do. Just change it from 50 to 30 and run the simulation. The difference is subtle. Is what we are doing here is to promote division faster, because you didn't change the growth rate, so the cells continue to grow at the same speed, if you want, and the division occurs before the other case. So you have something like this. I mean, it's hard to see here, but you should see that your cells are smaller because the division occurs at 30, and the growth is much faster than before. You accelerate the process, the growing process. The last modification now is this one. Now we are going to prevent the TD cells to divide. How do you do that? This is the part of the code here in the right window where you have the loop, or you are checking the cells to divide. Which cells are going to divide? But now we just want to the ST cells divide. How do you change the code? Please try. After change to 30, let's see the question here. My cell just dies after few steps. Well, let's come back to the the code, the change. The only line you have to change is this one. Anybody else has the same problem? Cell dying after division? Pedro, are you there?
Yes.
Can you see this?
In the breakout room.
Yes.
Caleb, wanna go to the breakout room? Just join there. I will be waiting.
Okay. Thank you, Caleb. So, coming back here. This is what we have to do. You mean, you change the rule for choosing the cells that you are going to check. You have here for cell in self-cell list, that loop runs over all the cells in your system. And you are going to change for cell in self-cell list by type. I mean, we are going to check only if the stem cells have the big volume above 30 to be included in the divided list. Included this in your code. Doesn't change anything else more. Anything else. But yeah. Okay, just even put it to run. What will happen? If you press I stop button just after the first division, you have two cells, the stem cells and the TD cells. But after that, you continuously have the stem cells and the TD cells growing indefinitely. See, there are no proliferation for the stem cells. Because it divides, when it divides, the parent cell remains and a TD cell is created. Things go on and the stem cells grows, reaches the volume of 30, divides, it remains, it creates a new TD cell. So you have a growing of only the TD cells. And only one ST cell remains in your simulation. Do you guys get that? Oh, yes, I forgot to mention this question here about cell type. Okay, if you did the answer, please answer the exercise. Please answer the the poll here. I'll give you a few minutes. Let's see the question, another question here. Ah, that's not a question, it's James' answer. Okay. Okay, advancing. Now, see, the pictures, the images shows that the grid, the domain is completely filled with, full with the cells, okay? So that will happen in any of your simulations today if you don't stop it. Because after reaching the borders, the cell have no space more to divide. And but even so, with the rules you have in your simulation, the target volumes will continue to grow, but the volumes will remain constant after some that stage being reached. Okay. In this situation, we say that our cells are under pressure, okay, because this pressure is how this pressure is measured. It's a difference between the target volume that has increased according to some rules and the actual volume that each cell has in that instant. Okay, we can derive this expression thinking a little bit about physics, okay? Because you know, or we know, that all force start with force. Force is a derivative of potential energy with its minus signals in front of it. And the CompuCell treats with energies. It's volume energy, surface energy, chemotaxis energy, external potential energy, lots of things. So if you vary energy, as CompuCell does all the time, we can extract from there a force from that particular energy term. So, on the other side, we know that pressure is the ratio between force and area. Which area? Well, I don't know. Maybe the things that are in contact here in the simulation. Okay, substituting this force here, the first equation, the second equation, the denominator here is A delta X is how the volume of the cells vary during the time evolution. So we have a pressure as a variation of the energy with the volume of the cell. Okay, this is how pressure is defined in physics. Here in CompuCell, which energy we are talking about? We are talking about the volume energy. This one, the term that it's include the effective energy from the beginning. When we include the plugal volume flex, you are including this kind of term in the calculations of the variations of energy. So if you use this value of energy in the above expression above here, you have that the derivative acts on this actual volume, that volume that varies in time. So if you derive, you have here the expression for the pressure in CompuCell. This is the way CompuCell implements pressure. Okay, there is this constraint and the difference between the real volume and the target volume. Question, let's see. Okay. So let's introduce this pressure in our CompuCell model. Okay. This pressure can reproduce what we call in biology of cell inhibit contact pressure. If the cell gets in contact too much, this contact prevents the cell to grow because there are no space between the cells to grow and to divide. We are going to use this pressure as this surrogate for the contact area between the cells. So we can say now that the target volume grows as a constant value as it has been so far, that's 25 or 500 Monte Carlo steps, or we can use it as a function of pressure to increase the target volume, like that. Here is a constant factor, here is a function factor of growth. So we can maybe choose lots of different ways to implement this function here. For example, here we have 3 different ways to implement this function: a linear variation, rational variation, no, it's not a Michaelis-Menten function here. No, it's not a Hill function here, like a Hill function, this third one. You can choose any of those two to try to reproduce your experimental the better you can, okay? The best you can. So, next exercise, implement the contact inhibit growth in the model we have. Let's start with the model, the previous model. But before you include that rule that only the stem cells can divide, go back to that situation. I mean, allow all the cells be checked for the division, okay, and add a plot window because we want to see how the average volume the cells evolve in time, and calculate this average volume. I mean, what is the average volume? Okay, you are going to run over all over the cells, sum all target volumes, and divide by the number of the cells. That's what you have to do. Okay, so here is the initial steppable as is so far, plus the loop over all cells, which is inside the mitosis steppable. And here is this regions where in the steppable that you need to modify. I think I don't remember. I don't remember if you saw scientific plots yesterday with Julio. Anyway, I think this one I'm going to do.
Yes, they did, but you should go over it again.
Yes, no, just checking if I would let them to include or I should include for them.
They should.
Okay, so do it. You do it now. Try to create the plot window, create the calculation for the average target volume, and plot the average value in the plot window.
Gilberto, how many more exercises do you have?
I think more 10 minutes.
Okay, cool.
Is that okay?
Yeah. I said we can go up until 1:30, but I've got to take over then for hackathon stuff.
Okay.
So yeah, 10 minutes sounds good.
I will go a little bit faster here. Maybe I let the last part for homework.
Sure, that'd be great.
So please answer the poll. Something is missing. I think I click. Oops. Okay, let's see it. I forgot to hit in that last slide. Here, in the start function is the place where you create the plot window, the graphical window, to make the plots. So you go to CC3D, into it, you go to the CC3D Python scientific plots 1 setup, and click, and those lines will be added in the start function. Actually, in reality, you have to put your cursor here in the inside the start function, and then click to implement those lines. Now you change the window title, the title of the x-axis, the title of the y-axis, make the x scale linear. Sometimes you can choose logarithmic, for example, for both scales, x and y, and put grid equals to true. Then we can see the grid on the plot. Then this last line is, how do you call this window plot? See here, average vol is the short for average vol. You're gonna plot using dots in red and with size of 5 voxels or pixels. Okay, this is where we create the window. Here, you make a small code to calculate the average vol. How do you do that? Well, vol, average vol, equals to 0. You define a variable here that where you're going to store the average vol for all the system. Then you measure the length of the cell list. I mean, how many cells exist in your system? You measure that, measuring the length of your list of cells. This is the way. So you have average vol, the variable, and the number of cells. This loop here is where you calculate the average vol. You do a loop over all the cells in the cell list and increase the average vol that is put to 0 at the beginning with the cell target vol divided by L. When you finish this loop here, you already have calculated the average vol for the cells in your simulation. Next, you add that point, this value of the average vol in your graph. See, you have to add this line here. Again, you go to scientific plots in CC3D Python. Now you choose number 2 in that drop-down menu. Click it here. Change the name that is put in default to use the same name you created the window in the first box here, AVVol, and add the point. This is the point at MCS, that is the value of the MSS that where the average was calculated, and the value that was calculated, and that's it. So please do it, include those lines in your code now, please. This is a little bit longer. I wait a little bit more there. Okay. Let's see what happens then. Now we run the simulation. You are ready to run it. Let's wait a little bit. This is what you should have seen. Let's explain. See, here I have three differences time pictures, Monte Carlo steps, and see this first two columns here. I have the blob growing, and in the window for the average target volume, we have this constant growth and coming back to small values because we have the cells are growing, divided for a long time. So in the second column is still growing, divide, but see the average value is starting to not start, but I think the growth will start to decrease because the space in the domain is becoming full, is becoming hard to grow. In the last column here, the domain is completely full, and the average target value grows to the infinity. If you don't stop the simulation, this last line here grows to the infinite. It doesn't stop. But there is no more division. So you can see here what's going on with the target value of the system. If you have uncontrolled division, cell division proliferation. The pressure. Now we are going to see what happens with the pressure in the cells. Let's say the following. Here, you initialize an entry in the cell dictionary called pressure. Okay, And let's do the same kind of things to observe the pressure in a plot window. I mean, let's create a new plot window to see the pressure, the average pressure in the cells. Okay, we have to create a new window, a new plot window, to create a new loop, and not a new loop, but a new line here to calculate the pressure, and to add another line to plot the pressure in this new window we created above. Since we are going out of time, I will show the results right now, okay? Because otherwise, Hayden is going to kill me. Okay, how do you create a cell dictionary? Here, in the initializer, in the steppable, the initializer is steppable. When you introduce the cell target volumes, the cell lambda volume, you create the dictionary. We'll call this dictionary pressure. A dictionary is something that you attach to the cell properties. It's a property that you attach to the object cell, which
The
has an
dictionary,
ID.
Gilberto, the dictionary exists. You're only creating a key entry for it.
Okay, but I'm talking this later, just a second. This is, we are going to calculate by hand the pressure here, just to see. Okay, so you create the pressure dictionary here. Then you create a new plot window here, as the same as before. I mean, the setup in the start function with new name for that window. See here, AV press. Now you create a new variable to calculate the average pressure here. And here you do the following. You update the cell dictionary inside the loop using that expression that we demonstrated before, the derivative of volume energy. Remember, 2 times lambda volume times cell target minus cell volume. I mean, the actual volume minus the target volume. And then you divide this value by L, which is the number of cells, and update the average value A pre that I created here. This is the same procedure that we have made for the average volume, with the difference that now you have this dictionary here. And finally, you add a line where you call, you put the point that you just calculate in the window that you created before. Look, we have, when you create a new self-plot window here, you have to put a different number here. See, this is win. The first one was win. The second is win2, because it's a new one. You have to have different names here. So, and here, when you add the point in win2, which is called AV press. Okay, now we put it to run. I'm gonna advance. So you still have that growth, because we didn't control yet the growth rate as before. But you can see here that the average pressure also grows linearly, indefinitely also, with the growth of the target volume, the average target volume. Okay, so if you could do that now, please try to go to introduce this modifications in your code in 3 minutes, I think, and put the simulation to run to see if you get these 3 windows working properly. And get this.
Can you go to the previous slide once?
Show the previous slide?
Yeah.
Okay. The one with the code? Here?
Yes, thank you. Okay, got it. Thank you.
Okay. Do you guys get that? Or need more time?
Maybe use the poll.
I am using the poll.
I just relaunched it.
Huh.
Hayden, I'm not a co-host since energy fell here.
Okay.
I had to enter again.
Yeah, I think James might have to do that. Let me see.
Oh, maybe only James can do
Yeah.
this.
Okay.
Is there any chance you can go back to the previous slide? I've missed a bit. I've got half of it working.
Sure. This one?
Yeah, that's what I want to do.
We do need to move on to our hackathon session here in a couple of minutes.
Okay, I'm
Gilberto,
gonna
so
pass this one. And I have to say that, as James pointed out, this way we implement the pressure is already included in the CompuCell, but I was doing it as an exercise. Pressure is now reached by using cell dot pressure. The same way you write cell dot volume is cell dot target volume, or any cell property, you can use cell dot pressure to calculate the instantaneous pressure of the particular cell you want to know. Okay. Finally, we are going now to change the way that growth happens. How do you do that? Well, we have to control the cell target volume growth in the steppable. Remember the line cell target growth plus 25 over 500 or 100, I don't remember. So you are going to change this growth to include this function as a control for the growth rate. I mean, the growth rate will be function of the instantaneous pressure of the cell. So how do you do that? You change that line, this particular line here, to multiply this growth, which the one which we have there. I think it's 25 by 500. That is in the code I was showing. This one, and you choose a function like is a maximum between 0 and this FP, which is P of reference and the instantaneous value of this pressure on the cell. But here we have a degree of freedom here to choose which value you should use to P reference. So it's by chance you can check the average pressure from your simulation, for example, before to include this function, and use that value. So you have here, for example, 35. So this function max always will give you, as a result, the biggest value between those two values here. 0, oops, I clicked with, and P half minus cell pressure. So it's never going to be negative. I mean, this is to prevent the cell to be his target volume decreased. So either 0 or a value bigger than 0. Okay, this is what we choose to implement this way. Since I already clicked it by chance here, with this grow, we have this behavior in your simulation. Do that. Include this modification in your code and put it to run. You're going to see this kind of behavior here. Oops, another one.
Gilberto, are you supposed to be screen sharing NanoHub or just the PowerPoint?
Just the PowerPoint.
Okay.
Since the beginning. Okay, guys, did you get that? Quick question for people. No. Okay. That ends the exercise. So you have here the average target value starts to stabilize here according with the growth of the pressure. I mean, the pressure will also attain a more stabilized value if you keep the simulation running a long time, which is not the point so far, but we can see that we can control the growth of the average using the pressure the cells have. Okay. To finish, I would suggest that you do as a homework to try those two different functions to control the growth rate. Use these functions, the left one, substitute the previous one, put the simulation to run. This is the behavior of the simulation, the function of the pressure. And here is the Hughes function, okay, with one more degree of freedom, which is the power of the Hughes function here, n. You have to choose. This power will change here the length, I mean, the derivative of the pressure curve here. It's going to be more slowly or more peaked around the zero value here. Okay, try that for homework.